Alrighty, let me pull up our practice exam here. It should be exam 4. Yes. Alrighty, and let's see what we've got here. Alright, so it looks like all of the questions are from Rebecca, which is fine. Alright, so let's see. We're going to start, I guess, with number 4 then. So let me have that over here. So I have it. Okay, let's go through it then. Alright, so number 4 is a stoichiometry problem, right? So we have, hopefully by this point, we will have done the reaction. Remember at this time, at that semester, students would know if they got the things correct. Their first, on their first, like they would see if it's correct or not, so they would know the formula for the reaction. So let's just make sure that we have that right. So I'm just going to go ahead and assume that all this is okay. All right. So how many mils of silver nitrate is needed to react with blah, blah, blah. Okay. So we are given information about the copper 2 chloride. We're given that we have 100 mLs and, 0.30 molar. And then we know that we have 0.25 molar of the silver nitrate. So this is what we're figuring out here. The missing part will be our volume, right? So we have enough information about CuCl2. So that's where we're going to kind of start our plan here. All right, and then so it looks like with both of these we're dealing with molarity. So molarity, remember, takes us to liters. And then we can go to milliliters just using the metric system. And in this case, it's going to be the same on the other side because we're given a volume of copper 2 chloride. And we can go from ml to there. Just so you know, for this one, because we're doing with, let me not even do that. I think that might just be more confusing. So never mind. So of course, in the middle is our reaction coefficients as our conversion factor. Here we have the molarity. There we also have the molarity. And then we just have metric stuff for the last ones. So let's go ahead and do it. We have 100 ml. Oh, I didn't even do the liters part. Well, hopefully we can see that 100 ml is 0.100 liters. I mean, that hopefully you can do in your head by this point. This is CuCl2. And then we have our molarity there. Alright, so we have all this. Gotta find our calculator here. So 0.1 times 0.3 times 2 divided by 0.25 times 1,000. Doing this, we get 240. However, we're going to need to round this to the appropriate sig figs. Actually, that is 240 with just 2 sig figs, so we're okay. We just need to get rid of the decimal there. And that is our answer. And so it looks like the answer should be D for that. All right. as questions come up, feel free to put them out. Alrighty, so next one will be number 8. This was number 4. Number 8 is another stoichiometry problem. Of course. Yeah, and if there's any on those practice things that you guys were confused about, we can do those too. So post it in Discord. We'll take a look. Alright, so for this one, we're going to need the reaction again. Okay. Alrighty, so it looks like we're given 3.6 grams of iodine. And we're asked for liters of the gas that's produced. We have pressure is 1 atmosphere. Okay, cool. Eddie, we'll look at that after. 1A. Okay. Yeah. Alrighty, so we have all this fun stuff. So we know we can get moles of iodine. That's the one we know about. We're also told in the problem that iodine is a limiting reactant, so we don't have to worry about calcium chloride. And there's not even enough stuff in the problem about calcium chloride anyway, so we couldn't use it even if we wanted to. Alright, moles of I2 to moles of Cl2. And then we're going to have our problem is asking for liters of Cl2, which we can go because it's a gas. Gases, remember, we can go directly there. And we're given grams. Grams, we can know how to get to moles. In the middle are reaction coefficients. We have the molar mass of iodine here. And then it looks like we're asking for volume. So we have our ideal gas law there for that part. Alrighty. So 3.6 grams times. Let me check what iodine's atomic mass is. 253.8. Okay. Our reaction coefficients are 1 and 1. And then if we are going to do this, we need to multiply our moles by RT over P. And pressure is 1 atmosphere. So let's do it. 3.6 divided by 253.8 times 300 times 0.08206. We get our answer here, 0.349. And it looks like we have 3 sig figs. One of the answers there is 0.350, which is fine. There must have just been some like slight rounding or something going on there. And so that's okay. Ta-da! So the answer for that one was E then. Alrighty. Next is number 15. Let me guess, that's a stoichiometry problem. How did I know? Okay. Alrighty, so we have decomposition here. Did I skip any? Did she? Nope, we did say 11. Okay, so never mind. I should have known. Always the last one, yes? Alright, change in enthalpy is negative 3752.39 kilojoules per mole. grams of oxygen, and then we have some we're given negative 2000 kilojoules. Oops. Just start. Okay, so with this, let me just check what the coefficients are supposed to be, because that will be important for us. So let me just check the key real quick. So again, in the previous problem, other students would have done that. All right, answer key. Let me switch to you. We really only need the coefficient for oxygen in this one, but we'll take a look. Okay, so looking at number 10 then. So number 10's answer gives us a coefficient of 17 for oxygen. So let me just write down the formula here. So we have C6H10, 2 of those, plus 17 oxygens, turns into 12 CO2 plus 10 water. Okay, so that's our balanced reaction. Alrighty, remember that delta H will equal any of these. So when we're dealing with this, we've got our 2000 kilojoules. We have delta H. And we have our 17 moles of oxygen. Remember, this is just our reaction coefficient over delta H. And then we're looking for grams of oxygen. So we will need to do grams. Oops. This will give us moles right here. All right, bust out your calculator. 2000 times 17 divided by 3752.39 times 32. Doing this, I get 289.9. Looks like we do have indeed 4 sig figs with all this, so that is our final answer. That one is D there. With this one, hopefully we can okay, fine, we'll do a little bit of logic with this one. So worst comes to worst, you're out of time, you have no time to do the actual calculation. We can eliminate some of these answers. So we know that oxygen's molar mass is 32, right? At the worst case scenario, this 2000 kilojoules is just about half of the delta H that's given to us. If we were to divide them, let's say it's like about 1.8 or whatever, but if we say it's roughly about half, like there's no way we could make less than half of oxygen, less than half a mole of oxygen, right? Just looking at those two numbers, since they're roughly twice as big as each other. And so if oxygen's molar mass is 32, there's absolutely no way we could ever make less than 16, and that's assuming a coefficient of 1. So right away, off the bat, you can get rid of answers B and C there. And chances are E is pretty close to elimination, but that would be assuming a coefficient of 1, I think. So that's just some things you can do. You can kind of think about things a little bit logically. Like, is there any way to get that low of a mass if you're using about half a mole? Not really. So it's always a good idea to kind of think about the reasonability of your answers. For example, in 15, we see that we have one of the answers here. We're heating 125 grams of calcium carbonate, and we have a yield of roughly 75%. There's no way we could produce 125, right? That would be, in fact, way over 100%, because we have two products there, so we're actually losing mass over it. So, just think about things logically. So there's a couple answers. If nothing else, just think about it and be like, okay, what can I get rid of? Test taking strategies here. So, all right, 15. CO2. Yeah, excuse me. So we have 125 grams of this. We're looking for grams of calcium oxide. And then we have a 78% yield. Remember, a 78% yield means only 78% of your starting material will react. If you want to use it at the start, you can. If you want to use it at the end, you can. I like to do it at the start just because I don't have to worry about... I like doing things up front, I guess. So with this, let's plan it out. We have information about that. We're looking for information about that. We're going to grams because that's what the problem said, and we're starting with grams because that's what the problem said. So for this, molar mass. Nope. This is our reaction coefficients. We have our molar mass. Molar mass again. Alrighty, so let's see. I think calcium carbonate's molar mass was the 100.09. Yep, there it is. So I'm just going to start off by doing the 78%. Of course, if you would prefer to do that at the end, that is just fine. The reaction coefficients we have are all 1. And then we have our calcium oxide, which will have 56.08. All right, let's do it. 0.78 times 125 divided by 100.09 times 56.08. Doing this, I get 54.6 grams, which is answer E, apparently. So far, answers have been D, E, D, E, so that's been very lucky for us. So apparently, when all else fails, guess D or E, or alternate them. So, alright, next is number 17. Alrighty, so another stoichiometry problem. Alright, we have enthalpy of reaction. Delta H is 28.5 kilojoules per mole. Is it exothermic? And then how much heat is blah 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 with moles of water. Alright, so delta H being positive, if it's positive, that means it's endothermic, right? That's what we remember from chapter 6? I don't know, whenever we talk about phase changes, remember if delta H is positive, that's endothermic. So we've already eliminated 3 of the potential options there. And now we're dealing with 2.5 moles of water. So this reaction is already balanced, it looks like, for us. So we're given 2.5 moles of water. We have delta H for 1 mole of water. That's our reaction coefficient. And just looking at the options here, our options are 11 or 71. So I'm going to say 71 because I don't want to actually do the math, but that would be our answer there. All right, so remember this delta H as a conversion between moles and energy. So in this one you had moles already. And so, yeah, cool. Fast one there. That was 17. The next is 21. The next stoichiometry problem. Alrighty. Okay, so how much aluminum is produced if that much zinc reacts completely? Okay, so we have aluminum nitrate plus zinc turns into zinc nitrate plus aluminum. I've balanced it as I've gone. Okay, so we have 25 grams of zinc, 3 grams of aluminum nitrate. No, I'm sorry, 3 grams of aluminum. So we have moles of zinc going to moles of aluminum, going to grams of aluminum, and we're given grams of zinc to start. That's molar mass, reaction coefficient, and then molar mass. So 25. It says it reacts completely, so we're doing 100% yield. I'm going to look up the atomic masses in just a sec, but I'm going to get the rest of this set up first. Okay, so where did I put my little book? Alrighty. So, atomic mass of zinc, 65.39. And then for aluminum, we have 26.98. Alright. Calculator time. 25 times 65.39 times 2 over 3 times 26.98. Doing this, we get 6.88, I'll say. If we have 3 6 is that one of the answers? Yes, it is. This time it was C. Hooray! Alrighty, and then 31. Alrighty, we have all of this, the last stoichiometry problem here. Alrighty, we're asked for ferric sulfate. So ferric sulfate, this is a time that I had actually talked about ferric and ferrous. Ferric is iron 3. So that's this compound. Ferric sulfate is this. Calcium bromide is our other one. Remember, for a double displacement reaction like this, our charges do not change. To balance this, okay, there we go. This is aqueous, solid. Hopefully we know that the calcium sulfate should be solid. Alrighty, so we are asked what concentration in molarity, what's the molarity of our iron 3 sulfate? And we used 28.9 mLs of it. And we produced 940 milligrams of the calcium sulfate here. It says the solid product, so that's going to be our calcium sulfate there. So, alrighty. so if we want to look at this, we are going from moles of calcium sulfate to moles of, oh gosh, complicated formula compound. And we're going to remember with this sort of thing, when we're calculating molarity, we're just going to want to stop at moles because we just have to do moles over liters in order to do this. And it looks like we're given grams of this, or milligrams, but we can very easily turn that to grams. So let's go ahead and do this. Alrighty, so uh, 0.940 grams. Again, I'm zipping through that metric thing. That should not be too bad for you guys. Calcium sulfate's molar mass. Is, where are you? 136.14. Our reaction coefficients were 3 for the calcium. Oops. And for the other one, 1 mole of Fe2SO4 Doing this, 0.94 divided by 136.14 divided by 3. Alright, we get 0.0023 moles. And we've been told, remember that molarity is moles per liter. So we have our moles there. We have some liters as well. I'm just converting the milliliters to liters again. Hopefully that's okay. So I'm going to take my answer divided by 0.0289. And so our answer is 0.0796. With that, do we have 3 sig figs, or what do we have here? 940 only had 2 sig figs, so we're going to need to round this to 0.080. So we just had 2 sig figs there. So I need to get rid of that 0. Okay, there we go. Alrighty. And then the fireworks problem. Oh, the true false stuff. Alright. Okay, so alright. Was there a particular one that we wanted to do on this? Or all of it, I guess? I mean, these ones are usually not too bad because it's just true false. Alrighty, so the limiting reactant is sulfur. It looks like we have 3 moles of sulfur and 3 moles of carbon. Carbon, though, has a coefficient of 3, so we're going to use up all 3 moles at once, but we're only going to use 1 mole of sulfur. So that one should be false. Carbon will run out first. So that's the case there. Theoretical yield is going to be 132, so let's see. 132 grams of, or no, I'm sorry. We have our 3 moles of carbon. We have a coefficient of 3 for both carbon and CO2. CO2's molar mass 44.01 grams, 1 mole. Do it just, okay, I'll actually do it. 3 times 44 is 132. Right, so that's true. percent yield of the nitrogen is 10%. So if we do this again, one mole nitrogen times 28.02 grams. So that's just 28.02. It looks like our actual yield is 25 grams, according to the problem. Well, that's definitely not 10.8. Hopefully we can see that. That's something like, I don't know, 85 or something percent, or 90%, something like that. So that one's definitely false. If we put some amount of potassium sulfide into water, it should dissolve. Yes, that's true. Anything with potassium should dissolve. Number of oxygen atoms in that many moles of KNO3. So we have 4 moles. We have 3 atoms of oxygen per mole KNO3. Oh, 3 moles rather. Times Avogadro's number. So let's say 12 times 6.022 percent to the 23rd. 7.226 times 24. Yeah, that's true. Name of this potassium sulfide is dipotassium monosulfide. No, definitely not. Nitrogen is a diatomic element. That's true. N2. Sulfur has 16 electrons. That is also true. If we look at sulfur's atomic number on the periodic table, it's 16. This is an endothermic reaction. That's false. We see that energy is a product. That means it's exothermic. It's giving off energy. And then 41, 25 grams is equal to 2.5 times 10 to the negative 13 picograms. That's false because picograms is the smaller unit. Remember, if you have a small unit, you have a big number. Big number goes with small units. So we can't have small number with small unit and big number with big units. So that's false there. It's probably positive 13 for that. So, alrighty, cool. Let's take a look at Eddie's then. So he wants to do 1A from this homework. Okay. Let's pull it up then. Where are you? Okay, 1A. Write the reaction, include states of matter, and balance it. Okay, so we have sodium bicarbonate and oxalic acid. So let's just write out the compounds. Alrighty, so we have those two. Hopefully we can tell this is an acid, right? And this is an ionic compound. Remember, 2 compounds put together like this means it's a double displacement reaction. When we're doing things like this, it's a double displacement. All right, so we can identify 2 ionic compounds together. That's a double displacement reaction. Always, always, always. All right, so if it is a double displacement, we're going to have to swap our components here. So we're going to want to put sodium with oxalate. Okay, let's just get rid of this pesky line. If we put that together, we get Na2C2O4. We know that's going to be aqueous because it has sodium in it, right? We don't care about anything else that has sodium. It's aqueous. End of story. No discussion there. All right, the other one, we have H plus and HCO3 minus. Remember, acids give H plus, right? For now, that gives us carbonic acid. But remember that carbonic acid is one of our special ones. That's going to break into water and CO2. But let's hold off on that. It's going to be a lot easier for us to balance this equation before we break up the carbonic acid. So let's balance it first, and then we'll go ahead and break it up. Okay, so if we kind of make a table here, we've got our reactants and our products. All right, so remember, you don't want to mess with polyatomic ions. It's going to make your life harder if you do break those up. So it's best to just keep them as is. So on the reactant side, we have 1 sodium. Product side, we have 2. We have 1 bicarbonate on the left, 1 bicarbonate on the right. Consider that carbonic acid is HCO3. Think about it that way. So we have 1 carbonic acid on the right side. On the left side, we have 2 H pluses. Here, we could even think of them with their charges if we wanted. On the right side, we have the 1, because we're looking at this guy here. So we just have 1. And then the oxalates, we have 1 and 1. So if we want to balance this, we're going to need to, let's just go down the line. We're going to want to change our sodium to 2. That will also bump our bicarbonate up to 2. So if we need to fix that on the right side, we need to make that into a 2. Oops. Which will also end up changing our hydrogen. And now we have everything in balance. So let's kind of just rewrite it now with the correct stuff. So is it oxalic acid? Okay. We're going to get out 1 mole of sodium oxalate. And note we have 2 carbonic acids now. Each one breaks into 1 water and 1 CO2. So if we have 2 of them, that's going to be 2 waters and 2 CO2s. So typically the things that students get confused with on things like this are trying to balance it after splitting up the stuff. That's harder. I would balance it first and then split stuff up. And then another thing is when you have compounds with H's in them, they can be a little bit tricky. So sometimes it's helpful to think of certain molecules as, for example, water. It's helpful to think of it as HOH. Because if you want to say something like NaOH plus sulfuric acid, when you're balancing this, it's tougher, right? Because you say, okay, well, look at all these H's I have on that side, But if we think about it as HOH, that makes it a little bit easier for us to balance. Right now, for example, we have one of each on our product side. Yeah, we could even do this. Is that actually, it's an identical type of reaction. We're going to end up with the same coefficients as the last problem. But that's okay. If we do this, we have two OHs now. If we need to have two OHs, we need to have two of these guys. Or rather, two waters. Here, let's just get rid of that. Which brings our H's up to 2 as well. And so, similar thing here. So, whenever you see compounds with multiple hydrogens in them, you kind of want to think about where they're coming from. So, this part of the water molecule comes from OH. And then the other part of the water molecule comes from that H, from the sulfuric acid, just like it did from this problem. So some of your carbonic acid H comes from bicarbonate, some comes from H plus from the oxalic acid. So if you can kind of think of it this way, that's going to just help keep you sane. So otherwise, it'll be a little bit tougher to balance. I mean, it's still doable, but it's easier this way. All right, Eddie, how was that? Alrighty then. Do we have any other questions that we'd like to go over? Let's see. Alrighty, well, if that's it, good luck everyone on your exam on Monday. Do not forget your homework is due Saturday, so make sure you get it in. Okay, I'm glad that helped. So make sure you get it in on Saturday. The homework key should pop up at 9 a.m. on Sunday. So if you are gonna turn it in late, make sure you get it in before 9 a.m. All right. So if you need to turn it at 3 in the morning because it's taking longer than you thought it would, you can still turn it in. Okay, so it's a big assignment. It'll be very useful. Don't forget there's all those practice things for predicting the type of reaction and balancing, as well as like some of the redox stuff. It's all on Canvas for you guys. So spend some time with those. It'll be useful. Your exam, I think, is I've given a little bit more time. I think I've given 90 minutes this time because I understand the math can take a little bit of time. So we're extending that a little bit. So with that, I'll go ahead and put these up. But other than that, yeah, have a great weekend. Study well. And I will see you on Tuesday for our acid-base beginnings here. Alrighty, so notes are up. So we'll see you guys next time. Enjoy your weekend.